Welcome to Module 8. In Module 8, we'll talk about fluid mechanics. So in this lecture, we're going to discuss three sections: fluids and buoyant force, fluid pressure, and fluids in motion. So let's start with fluids and buoyant force. So in this, we're trying to define a fluid, distinguish between a gas and a fluid, determine the magnitude of a buoyant force exerted on a floating object or a submerged object, and explain why some objects float and some objects sink. So let's take an example of how to define a general fluid. So a fluid is a non-solid state of matter in which the atoms or molecules are free to move past each other, as in a gas or a liquid. So a fluid is basically defines both a gas and a liquid. So both liquids and gases are generally considered fluids because they can flow and also they can change shape. So, and one of the characteristics, the differences between a liquid and a fluid is that liquids generally have a definite volume, while gases do not have a definite volume. So let's talk about density. So density refers to the concentration of matter of an object, is generally called as mass density. So it's generally defined as mass over unit volume. So mass over volume of the substance, so denoted by rho. So it's over mass over volume. So next, let's talk about buoyant force. So what does buoyant force represent here? So buoyant force is the general upward force exerted by a liquid on an object immersed in or floating on the liquid. So buoyant forces can keep objects afloat. So think of it this way. Let's say you have a bucket of water, and let's say you're trying to force an object to be submerged into the liquid. Now the liquid applies a return force. So that return force is the force of buoyancy. And the force that generally acts is the gravitational force, and the upward force is the force of buoyancy. Now the careful understanding of buoyant force and the gravitational force and the relationship in terms of the liquid refers to the buoyant force. So buoyant forces are the ones that keep of an object afloat on water, submerged in the water. So next, let's talk about displaced volume of a fluid. So generally, when an object is inserted into the liquid, it increases its volume. So which means that the liquid generally drips out. Let's say, for example, we have a system where we have filled the liquid up to a certain point where if it exceeds, it generally drops to a container. Now, when you put the solid into the liquid, you start noticing that water drains out, and the idea here is to understand the Archimedes principle. So what does the Archimedes principle state? So it states that the volume of the object is equal to the volume of the displaced liquid. So it says that the volume of the object is equal to the volume of the displaced liquid. So Archimedes principle also describes the magnitude of a buoyant force. So any object, what does the Archimedes principle state? So it states that any object that is completely or partially submerged in a fluid experiences an upward buoyant force equal in magnitude to the weight of the fluid being displaced by the object. Now notice that this is the volume of the fluid that is being displaced, so which means that this is the amount of force in terms of the mass. So the amount of mass of the liquid that is being displaced is so the weight of the fluid that is being displaced is the amount equal to the buoyant force. So Fb equals Fg of the displaced fluid, which is the mass of the fluid times the acceleration due to gravity. So in simple sense, the Archimedes principle is that magnitude of buoyant force is equal to the weight of the displaced fluid. So now let's talk about continue the topic. So for a floating object, the buoyant force generally equals the object's weight. Now there is what we call the apparent weight. So apparent weight of a submerged object generally depends on the density of the object. So for an object with the density, for example, rho naught, submerged in a fluid of density rho f, the buoyant force Fb obeys this ratio. The weight of the object over the buoyant force is equal to the density of the object by the density of the fluid. So Fg, the weight of the object, over the buoyant force is equal to the ratio of the density of the object to the density of the fluid. Let's take an example problem and understand how this works. So what is given here? A bargain hunter purchases a gold crown at a flea market. After she gets home, she hangs the crown from a scale and finds its weight to be 7.84 Newton. And she then weighs the crown while it is immersed in water and reads that the scale says 6.86 Newton. So they're asking you if the crown is the crown made of gold, and they're asking you to explain the final answer. So let's take into consideration the data that is given. So the first thing that we need to remember is the weight of the object is 7.84 Newton. Now remember that when it is submerged in the liquid, the amount of weight is equal to the buoyant force. So that buoyant force is 6.86 Newton. I'm sorry, this is the apparent weight, not the buoyant force. So this is the apparent weight. So when you're submerged in the liquid, let's consider this is the object. So you have two forces that are acting. So one force is the force of buoyancy and the other force is the weight of the body. So the apparent weight of an object is the net difference between the two forces. So which means that here apparent weight is the difference between FG and FB and FG. Now so because the weight is actually higher, so we have to take into consideration that this is actually FG minus FB. So FG here, so apparent weight is given as 6.86 Newton is equal to FG is 7.84 minus FB. So FB becomes 7.84 minus 6.86. So that becomes 0.98 Newton. So the force of buoyancy is 0.98 Newton. Next, we are submerging it into water. So which means that the density of the fluid here is 1000 kilogram per meter cube. So which is the general density of water. Now the one thing that we do not know here is the rho naught value. So now use the Archimedes principle. So which says that Fg of the object over the buoyancy force is equal to rho of the object by density of the fluid. So that is 7.84 divided by 0.98 is equal to rho naught is 1000 divided by rho F. I'm sorry, rho naught divided by 1000. So rho naught becomes 7.84 over 0.98 times 1000. So that value becomes 8 times 10 cube kg per meter cube. So which is about 8000 kilogram per meter cube. So we found out that the density of the object is about 8000 kilogram per meter cube. Now, how do you know whether it is gold or not is to calculate the actual density of gold. So when you take it from this table, the density of gold here is 19.3 times 3, 10 to the power of 3. Because the density that we receive, that we have from the answer is less than that of the original value. So which means that the crown here cannot be pure gold. So this is the idea behind the fluids and buoyant force. So next, let's get into the topic on fluid pressure. So in this, we're going to calculate the pressure exerted by a fluid. And second, we're going to try to calculate how pressure varies with depth in a fluid. So let's start with pressure. Pressure is the ratio of the force on a surface area. So force per a unit area. So generally defined as force by area. So we use the Pascal's principle that states that whenever a pressure is applied to a fluid in a closed container, it is transmitted equally to every point of the fluid and to the walls of the container. So remember that this is an important principle that we use a lot in nature. And let's take an example. So let's take an example of a car dealership where you see, you have a platform that's being raised. So you notice that there is a lever that is being applied here. So the force that is being applied, let's consider it F1. And the force that is being transferred, let's consider that to be F2. So according to Pascal's principle, the pressure at P1 must be equal to the pressure at P2. Let's consider this area is A1 and let's consider that this area is A2. So we know that from Pascal's principle, P1 equals P2. So when you write force, we know that it can be written as force by area. So F1 by A1 becomes F2 by A2. So if you want to find F1 by F2, we can write that as A1 by A2. So this is the idea behind Pascal's principle. Next, let's talk about pressure when you have submerged a body into the liquid. So pressure generally varies with the depth. So pressure generally varies with depth in a fluid. So the pressure generally increases with the depth, so which means that the lower you go into the fluid, the higher the pressure. So let's take into consideration a simple example. Let's say we have a container with a fluid and you have an object inside it. Now let's consider that you have liquid surrounding this object. So let's consider that this is the surface. So from the surface, let's consider that this is at a depth of h1 and the downward surface is at a depth of h2. Now let's consider that the total height is delta h. So the total height of the object is delta h. Now let's consider that the pressure here is P naught. So P naught here is the atmospheric pressure. So this is the pressure exerted by the air. So as we know that when you go deeper, you start getting more and more pressure. So how do you calculate that pressure? So we know that pressure is force over area. Now the idea here is to understand the topic of force here. Now one another way of calculating pressure is based on energy over volume. So energy over volume. So let's consider that this is the atmospheric pressure at a depth. So what happens when you start going towards the depth part here? So as you go more and more, so pressure P naught or the change in pressure is defined as rho g times h. So let's consider at this point where it's at the depth of h1. So we can consider that the total pressure at that point, let's consider that point 1. At that point P1, so the pressure is going to be P naught plus rho g h1. Next, let's consider the point 2. So this is point 2, this is point 1. So that's going to be P naught plus rho g h2. Now what would be the difference in pressure between the 2 points? So P1 to P2 minus P1, which can be written as delta P, can be written as P naught plus rho g h2 minus of P naught minus rho g h1. So P naught gone. So you end up with rho g h2 minus rho g h1. So rho g can be taken common and you get h2 minus h1. So P2 minus P1, which is also delta P, can be written as rho g times h2 minus h1 is delta h. So the height of the object determines the change in the pressure between the two surfaces of the body. Next, let's get into the final topic or final section, fluids in motion. So in this, we're going to try to examine the motion of fluid using the continuity equation. And second, we're going to recognize the effects of the Bernoulli's principle on fluid motion. So let's start with fluid flow. So moving fluids generally exhibit laminar flow or turbulent flow. So either they can be smooth or they can be irregular. Generally, an ideal fluid is fluid that has no internal friction and viscosity and is generally incompressible. So incompressible refers to the idea that there is no change in density. So whenever you see the term incompressible, remember that there is no change in density. So we use the ideal fluid model general to simplify the fluid flow analysis. So what are the characteristics of ideal fluid? First, it should be incompressible, which means that there is no change in density with respect to pressure, and they are non-viscous, and they also exhibit non-turbulent flow. So let's take the first one, principle of continuity. So let's take into consideration you have a surface, and let's say we have a pipe going from one point to another point. So let's count this point 1 and point 2. So let's consider that this area here is A1 and this area here is A2. So let me draw it much more realistic so that so let's call this area A2. Now let's say the fluid enters at point 1 and exits at point 2. Now the idea here is that let's say this enters with a velocity v1 and this exits with a velocity v2. Now in a given amount of time, let's consider that this is the amount of liquid that passes through it, and that amount of liquid will be the same amount that gets displaced here as well. So the idea here is that the mass that enters at point 1 is equal to the mass that exits at point 2. So we use the law of conservation of mass, so which means we can write that m1 equals m2. So we know that mass can be written as density by volume. Density can be written as mass by volume. So mass can be written as density times volume. So we are considering that this is an ideal fluid. So for an ideal fluid, there is no change in density, so which means that rho stays constant. So if it stays constant, which means that rho1 equals to rho2. So we can write it as rho v1 equals rho v2. Now let's consider the idea here. We need to have the volume. So let's consider that this liquid moves a small amount, the distance delta x1. This moves a distance of delta x2. So over a time delta t. So how do you consider the ideal condition here? So we know that rho get cancelled. So we get v1 equals v2. So let's consider v1 equals v2. We know that volume is area times distance. So let's consider the area is a1 times delta x1 equals a2 times delta x2. So now we need to know the distance. Now we know that velocity is distance over time. So we can write that v1 is equal to delta x1 over delta t, and v2 can be written as delta x2 over delta t. So from this we can write that delta x1 is v1 times delta t, and from this we can write delta x2 is v2 times delta t. And this becomes v2 times delta t. So now putting into the condition delta x1 and delta x2 values, we get a1 times, so this becomes a1 times v1 delta t, and this becomes a2 times v2 delta t. So delta t gone, so we get a1 v1 equals a2 v2. So from this we understand that a and v are related. So when you remove that proportionality, so we can write that av is constant. So this has a special term in fluid mechanics, so where it's called the flow rate. So Q here, flow rate is equal to the area times the velocity. So generally denoted by meter cube per second. So the unit is meter cube per second for the flow rate. So now let's talk about the principles of fluid flow. So we know that the understanding from the principle of continuity, so which states that A and V are equal to constant. So which means that if A increases, the velocity decreases, and if A decreases, the velocity will increase. So which means that, let's say for a simple example, let's say we have a small opening on one side and a large opening on the other side. So let's say if it enters with a velocity v1 and it exits with a velocity v2. So because this is a small area and here you have a larger area, so which means that here v1 is going to be greater than v2 because a1 is less than a2. So a here is inversely proportional to the velocity. So the area is inversely proportional to the velocity. So, or simply accurately we can more write it as velocity is inversely proportional to the area. So as the area increases, the velocity of the water that is coming out of the fluid that is coming out of the end will decrease. So this is the idea behind the principles of fluid flow. So the speed of the fluid depends on the cross-sectional area, and we use another principle to represent the pressure. So that principle is the Bernoulli's principle that states that the pressure in a fluid decreases as the fluid velocity increases. So now let's take into consideration this principle and let's talk about Bernoulli's principle. So what does Bernoulli's principle state? So Bernoulli's principle states that the sum of pressure energy plus the kinetic energy plus the potential energy of a liquid is constant. So the sum of pressure energy plus the kinetic energy plus the potential energy is constant. So this is called as the pressure equation. So there are other forms of the same equation. Another form is the pressure head equation, which can be written as P by rho plus half V square plus GH is constant. So this is called as the head equation. So all of them are derived from the same basic principle or the idea behind the conservation of energy. So remember that Bernoulli's theorem applies conservation of energy to liquids. So conservation of energy to liquids. So these are the two equations that we generally use for the Bernoulli's equation. So what do we use Bernoulli's theorem to represent? So the best example of this is the working of an airplane. So an airplane, the working of any fluid system. For example, the flow meters that generally use some version of the Bernoulli's principle. They are also used in medical devices such as catheters, where you have to know the actual flow rate inside your body. So, and that can be used, that can be a measure. And most of the IV materials, IV systems that generally use intravenous liquids require some form of monitoring the amount of flow. So that generally is done by using Bernoulli's theorem. So the devices follow the Bernoulli's theorem. So with that, we end the topic on fluid mechanics.